Hello there, welcome to another concept session, and I'll have some problem also at the end. So today we're going to do what you might consider dirty part of physics. It's not as clean as doing things in vacuum. Okay, so how do we Maxwell's equation, the way we write them, they are true universally everywhere, not just matter, outside matter. So let's write them universal. So universal looks like this, and I'm going to use SI units, although I really don't prefer SI units in my work. I'm going to use SI units. That has a charge in coulomb. So this is like a coulomb, meter, second, kilogram. So this is standard definitions like that. So in this SI units, okay. So the way we write down is we have at each point. So there's point P, and that's O, and at that point there's a vector R, and so what's happening at that point time t? So this is one frame. I'm not talking about frame to frame, just in one frame. We can write the equation. So this is the point P. So at that point, you may have charges here, you may have a current flowing here, it may be current flowing here and charges. Okay, so it's very arbitrary situation, and I want to know what's the electric field and magnetic field at point P. So what's the electric field at R at time t, and what's the magnetic field? Sometimes called magnetic induction in some literature. So this is R and t. We're just gonna call it electric field and magnetic field. Okay, and these so what are the laws, how they relate to some charge densities and some current densities? Okay, so at this point, maybe also a charge flowing through that point, so at that point, at that time, so let rho RT be charge density at that point, J RT be current density at that. This is the volume current density, is also called volume current. So if you don't know what this is if I'm looking in that direction, then how much a current passes per unit cross-sectional area, that's what that is. So how much charge per unit time passes per unit cross sectional area. So you take a small area, there's few charge, divide with the area. So it has a I current passing over area. So that's the unit for J, the current over area. Okay. Sometimes the I is, you say, I get a J over some area A dot the area, some surface through which how much current passes. This would be a relationship that you would use to get the current that passing through this in that direction. The area, if it's oriented like that, normal to the area is point. So this is like a normal dA. Okay, so that's the definition. And what is this? This basically, I go at that point I say how much charge per unit area is at that point, at that time. So everything is at that time. So we're going to write a point form. So here are the laws. Del dot E. So this is a divergence of the electric field, how the electric field is at this point, you know, how the electric field is diverging. So it uses a little neighborhood to check how the is diverging, is equal to 1 over epsilon naught, and this is a universal constant, times rho R of t. So I'm not going to write this out. It's already, I wrote them over there, so let's erase this. So everything is written at particular time and particular place. Okay. If you look at the del dot B, that's 0. So this one has a name. It's called Gauss's law, and this one has no name. And you might say Gauss's law for B. What it is saying is, over here, if I integrate over this, I'll get a charge, a plus charge and a minus charge value. And so over this side, it's saying that there are no magnetic monopoles, not corresponding plus charge or minus charge for magnetism. Magnetism always comes in a dipole, both plus and negative bundled up in one unit. You can't separate them. So sometimes people say this is kind of right side is 0 because we haven't seen any magnetic monopoles. There are electromagnetic theories where right side is not 0, and you can say, okay, what will happen if there was a magnetic monopole? Suppose there was something just at the North Pole or just at the South Pole. We haven't seen that, but you can ask that question, and that question was asked, and people look for it, and they haven't found it yet. But when they find it, this right side will be turned into non-zero. But the present understanding is that it doesn't exist in nature, but that can change, like physics is elementary. So now these are the divergences, and then there is a curl. So for any field, this field, if I give you both divergence and curl, then you can deduce all the other properties for that field, right? So that's a theorem. See, also you can see here over here, units of B and E kind of related. So you can say unit of B times this is 1 over time equals to unit of E 1 over length, which means unit of E equals to unit of speed times unit of B. So they're kind of, you can see the unit of E and B are related like this. So so they're not independent things. So this is called Faraday law. For some reason, people don't use Faraday's law. This is a Faraday law. This is like a Gauss's law. Okay, so now we need a del cross B, and del cross B used to be just mu naught current density J. This is you can say this is total charge density from all sources, and this is total, and that's what that is. That's the total. Now this turns out to be inconsistent. These equations, these three equations. This is called Ampere's law. And if you say that charge is conserved, like if I look at a box in a space and say, well, what's the charge density at time t? And then say, well, if the charge is flowing in and out, so its charge density will change. So this is time t, and this is time t plus delta t. So this will be depend on what the j is, and this is rho. So rho of t and rho of t plus delta t. So if you work this out, you find that del dot j must be equal to minus d rho dt. So that the charge is conserved. So whatever charge density is changed is accounted by how much came in and how much left. So this is called charge conservation law. Okay, so I haven't shown you this, but you can do this calculation. This will end up here. Okay, this calculation, if you apply it to here, so if you take del dot, so if you just apply to this guy over here, del dot del cross b, and on the other side mu naught is constant, so del dot j, this side is identically 0. So I actually, you already see this is 0, then this is 0, but this can be non-zero if more charge came in than left on the other face. So amount of charge came in from this face and amount of charge left at this face. So j just came in and j just on the face number 2. So there may be different amount came in and different left. Then del dot j won't be 0 because some charges will be either depleted or extra charges will be found, okay, in the box. So this certainly is inconsistent. So these two are inconsistent. And you can say, well, how can we make it consistent so that I can generate this? And then you see over here, if I could add mu naught epsilon naught dE dt, then these two will become consistent. This was noted by Maxwell. So let's see, if I were to add, the added term will give me mu naught epsilon naught, and dE dt will be, I took a del, and del and dE dt will commute, right? You can write like that. So bringing del dot inside, and this with this over here is rho. So this thing becomes mu naught del dot j plus mu naught d rho dt. Now left side is identically 0. So this setting this equal to 0, this equal to 0 becomes consistent with that. And so these are the 4 laws. So instead of calling it Ampere's law, you might say Ampere-Maxwell law. So this is true along with this, okay? This is stating the charge is a conserved quantity at any point in space. Any volume you take, a charge, you have to make sure that what comes in and what leaves has to be accounted for. And charge just can't just disappear in nothingness or things like that. So you can see lots of reactions where you have a electron coming in, and a positron coming in, they annihilate, but then they give out chargeless properties, maybe gamma, these photons come out. So they'll say, wait, I had charge, I don't have any charge anymore. But yeah, if you add these two guys came in, there's zero. You had a zero charge total and you have a zero charge in the end. And this is also at the heart of, when you're balancing chemical reactions, then you get that, okay? So this is universal. So what happens if we have a magnetic material or dielectric material? How do you handle those things, okay? So let's look at that. That's what this video is about. Okay, so suppose we wanted to do problems like, suppose I have a bar magnet. So this is a magnet and maybe uniformly magnetized. So it's got, say, a magnetization vector pointed that way. And I want to know what's the magnetic field out here. B in here, B out, B in. What's the electric field and things like that, okay? Say we have a sheet, a dielectric sheet which has lots of plus minus charge, but they are kind of bound. They're not putting their extra charge, but basically they're dipoles. Like say we have a water, right? Maybe it's a frozen ice, and water molecules are like a dipole, a tiny dipole, and a whole bunch of them here. And I want to do what's the electric field over there, what's the electric field over there, what's the electric field at a point inside here. How do you solve some problems like this? Turns out we need to broaden what we mean, okay? So let's look at a dipole thing. It's electric dipole. So if I had a single electric dipole, say in this coordinate system at some point, say as a vector r prime, and I want to know what's the electric field over there. So this is some kind of point dipole, electric dipole, with a dipole moment p. And the value of p is like q times, you have a minus and a plus, that q times the distance separated by them. And so we are not going to look at in detail, but just as some dipole moment. So what's the electric field there will be? So the way we handle this, this is r vector, and this direct vector is, you can write down like this. So the r is r minus r prime. So this is the point P. So B at r will depend on where this is located, but I just want V at r. This is fixed, and I want r to be any place. So this is the variable. So this will be equal to 1 over 4 pi epsilon naught p dot unit vector. So r hat is r divided by the, so this unit vector in that direction, r hat over r square. So what we do is take any of these model. So here's a dielectric material, and I want to know at this point. So how do we approach this? We do exactly the same way. We take a tiny piece, and we say it's got all kinds of we define a quantity, polarization density. So this is called polarization, what it is a dipole moment per unit volume. So if volume is say d tau, is going to do tau prime for the source, and say this thing is located at point r prime. It's exactly same geometry. This is r, and this from here to here is direct is r vector, exact same script r. So in this, the dipole moment is a tiny amount. It's going to be p d tau prime, p at that point times d tau prime. So we write p at r prime d tau for this quantity. So this dotted into r hat over r square 1/4 pi epsilon naught. So that's going to be electric field from just this over here. So at point P, so we're just going to dP. I want to get for the whole stuff, that means I need to integrate it. So this whole thing will become integrate over this volume V. Now this is kind of complicated stuff, so you can simplify further. Not electric field, it's a V at P, not electric field, electric potential. So the way we get electric field is we just del V minus del V if it's static. Otherwise, if it's dynamic, then we have to also have d dt of vector potential. But here, because it's static, this will be 0. And so you get V and you get this answer. So that's the way we handle this. No extra charges placed here. Okay. This thing actually can be broken up into two contributions from some extra, maybe charge density, different. The way the dipoles distributed is very different every place. So you can sometimes extra charges can be left over here inside, and or there can be some extra charges left over at the surface. So this is going to be a contribution from charges. We call these bound charges because we didn't put extra charges in volume, from bound charges volume plus bound charges at surface. So when we work it out, I'm not going to do that calculation, but you can show that V R will be equal to 1/4 pi epsilon naught, and instead of R, it's going to be rho B. This is the volume thing, rho B d tau prime over R volume plus 1/4 pi epsilon naught over the surface that's over here. So we just bounded surface which is surrounding the volume. Sigma B is the surface charge density. We just use the letter B to denote that this is, I didn't put extra charge, it's just because it was polarized over R. So what are the formula for rho B? So formula for rho B, I'm going to write over here, rho B is going to be minus del dot P, and sigma B is P dot n hat. N hat is the normal to the surface. Okay, so these are the contributions that come in. So if you look at here on the right side, what happened when we have material, I can separate this into 1/epsilon naught rho. So this is I put in extra charge present, not from a dipole, just extra charge density, and then a quantity like that minus del dot P. And you can see that then I can actually bring this on the other side. So I have a multiply with epsilon naught. So we can do del dot epsilon naught E plus P equals to rho F. And this quantity we define displacement vector. It's called displacement vector. Field. So instead of electric field, when you have a polarized material, we deal with the D field, and if you know the polarization, you can actually get the electric field. So we use D equals to epsilon naught E plus P. Okay. How about the magnetic field? So magnetic field, similarly, this J thing can also be, suppose I have a magnetic material. What do I do? When I have a magnetic material, say this is magnetic material, say you have an M in here, maybe a magnetized iron or something like that. So this will be magnetic dipole per unit volume. So just like P, this is actually a density of dipoles, and this is called magnetization. It's just a name for this property. So if I know a magnetic field for a magnetic dipole, we should be able to work it out. The answer is also very similar. So if I have a magnetic dipole, let's call it M at some point, and so it's some not at the origin but someplace else. So this R prime, and I want magnetic field over there. So that's, say, from there is R vector, and the field point is R vector. So this is the point P. Okay, so what's the magnetic field at P? So I'm not going to write that from this, more complicated. So we can write vector potential A at point P. So vector potential at point P can be easily written. So A at R is mu naught over 4 pi M cross R hat. R hat is unit vector there, just like we had it over there, over R square. So that's so how do I do over here for this stuff? Well, so we look at a small volume d tau prime and say what's the magnetic moment there. So dm will be m d tau prime. So this is the magnetic. So we just replace that. So from here, this is at r prime vector, and the field point P is r, and this r vector. Just complete analogy. So we can, over here we can write down A as a dA, and then that's going to be mu naught over 4 pi m for the dm. So m d tau prime across r hat over r square. So that's going to be from just this, and then to get the whole thing we need to integrate over the volume of this thing. So that's the volume. Now it turns out when you integrate this whole thing, you just like over there for V, it actually turns out to be two terms. And let me so this turns out into two terms, one from volume flowing current density plus from surface flowing current density. So because this is, I'm not just it is a magnetic material with just M over here, right? There's no real current. I'm not passing any current. So this is called bound current density. This thing is denoted by JB vector as a B for the bound, just like over here. And this thing is similarly denoted by KB. Now from here to there is a pretty nasty calculation. I'm not going to do it. You can see it in some advanced E&M book. The formula for JB would be that we will need is going to be del cross M, and K is K is equal to M cross N hat, because it is as the surface. Okay, and so this thing, when you write it out, is mu naught over 4 pi over the volume, and you have a del cross M d tau prime, and then 1 power of R plus mu naught over 4 pi the surface that bounds it. That's why it's like this, surface that bounds it, M cross N hat over R d tau prime. That's for the magnetic material. Okay, we are sometimes you're going to have a polarization changing in time as well. That also acts like a current density. So let me first put this thing in this equation and see how far we go. Okay, so I cleaned up a little bit to write that. This is called bound current density. I'm just listed over here. Okay, so, and this is the actual freely flowing current. And so it's called free current, which is when you like put a battery or something like that and the current flows. That's the density. And this is the not flowing, but because there's a magnetic magnetization, it acts like there is a current there. Okay, in formulas, and then we just call it bound current density. But then we suppose the material are also polarized. So if I have a polarization P, then this end, if the polarization changing in time, it's a function of time, then at some other time in the same amount of wire, and so this is this polarization at T plus delta T. If this is not the same as that, then you can see over here is P dot N hat. That's the sigma B on this surface, and on this surface is so sigma B to the maybe right and sigma B to the left using P dot N hat at this surface. They will be changing. and it as if a current is flowing. If that's changing, then as if a current is flowing. And if you let's say what the current will be, and we're just going to call it current because P is changing. And let me so this will just be equal to dp dt. And so this you can see why this will be the formula, right? Because what we have is sigma b, and the surface, let's call it surface dA, and it should be how much the sigma be changing. So if you look at this, the unit of this will be charge over time. So this is the amount of current that's going to be flowing. So the J corresponding to this, J corresponding to that will be just this divided by the area, d sigma b dt, and we just take out the n hat. We look at this in the same direction we're just looking at. So this is just dp dt. So you can trace the vector property and how the area is normal to the vector property vector. Okay, so you can actually introduce the vector, and so there's another thing here which is not, we don't include in the bound charger, but it is there, dp dt. If polarization changing, then it acts as if there is a current there. There's no current, but there is as if it's mathematically acts like it's another current term. Okay, so what do we do? So this equation, it looks like a very complicated, and if you remember, d was simply epsilon e minus p. So epsilon naught e is equal to d plus p. Actually, this is plus here. This is d minus p, not plus p. So we now look at what I can do. I can because this mu naught with this mu naught, so I can combine this with this much and bring this guy on the other side. And this equation can be written del cross, bring mu naught on the other side, one moment b, then bring m on the other side. So we have a del cross m come that side, and it becomes mu naught j, and combine these two, that just becomes dd dt. Now we say, okay, we are going to introduce a new field corresponding to that. So we say let h, I'm going to denote h this thing, this will be h equals to 1 over mu naught b minus m, and then I can write down in a more compact form is mu naught, this is the free part, j free part plus dd dt. So you have this equation, this equation, this equation, and this equation. So although it's a kind of a mixture of things, but we call that mixture of both E, B, D, and H Maxwell's equations in matter. Okay, let me clean up a little bit. Okay, so let's do this is my summary, and let's do an example of suppose you have a a sphere, this example, and it's got a polarization is given to you. Polarization is P0 and it's constant throughout, and a sphere is radius r. So what will be the what will be the rho b and sigma b? It's very easy to get, right? I can introduce a coordinate system, x, y, and z, and so this is an inside point, and this is a surface point. So this is P1, and it's called P2. Okay, so in inside point, I'm going to have a density. So rho b will be minus del dot p. So p here is simply P0 k hat, and so this is actually 0 because p is constant. So how about sigma b? Sigma b is going to point at the surface, and if you look at the n hat will be just radial, right? So sigma b will be just p hat dot n hat will be P0 k hat unit radial vector, right? And so k hat is that way. If this angle is theta, then this is just going to be P0 cosine theta. So this will act like you got no charge inside. So this is equivalent to a problem where you have this charge density only on the surface. So if I give you a spherical thing with this charge density, charge is varying, and I want to know what the electric field is there. What's the electric field is at inside point? You should be able to do this problem, right? So what's the electric field at that point? So you can do some area element, and from that area element you have in that area element the amount of charge will be sigma b area element, and that area element can be, from there you have an r, and this area element has an r vector, and this is r vector. So you can see that I can actually do electric field. We can do potential at that point. Potential at that point will be simply that sigma b dA over r, and sigma b depends on cosine theta. So this and 1 over 4 pi epsilon naught. And so over this surface we need to integrate this, and the dA will simply be the radius r, sine r square sine theta d theta and d phi, and sigma b will simply be P0 cosine theta, P0 cosine theta. So you need to do this integral, and then you get the potential at point P. And once you get the potential point P, that information of this x, y, z, so this will depend on x, y, z, and where this point you locate, that's going to be some x prime, y prime, z prime, and these are all from the prime, and this is primed. And we need to do this integral, and then in principle you can do it, right? It's really not that hard to do. I'm just going to leave that like that. So where does this come from? This come from just treating it like this. I didn't even do anything, right? You could say another way is, if you give me a P, I don't have any charges, then I have del dot D is actually 0, and doesn't mean D is 0, okay? And then over here B is all 0 here, so we can say del cross D, I can just E is equal to D minus P over epsilon naught, that will all be 0, equals 0. So del cross D equals to del cross P. Okay, so I can use this to actually get the information about what the D will be. Okay, and from the D we can figure out what the P will be. So I'm not going to go into more detail on that at the moment. Okay, so very quickly let's look at another example. So this is an example of how to use, say, H. Okay, so if I have a if I have a some magnetization M, using these I can quickly say this is equivalent, this is uniform, so in no current inside, JB is 0, but then as if there's a current flowing on the surface, and so K, this is KB, at any point is equal to this M cross N hat. So if you look at any point here, point on, which is angle theta from the z-axis, and maybe in the xy plane it is phi, this x and y. So the n hat, so you have m k hat. So this direction will be r hat, and so it's going to be in the direction, you can see it's going to direction the phi hat, it's going to be m phi hat. So this becomes a problem if I want to know it's kind of like if I give you a sphere, a charged sphere, and is rotating so about z-axis. So suppose I put charge on the surface of it, it's a metal surface, and I'm going to rotate it, then that problem is equivalent to that problem, and that problem is solvable. And over here we can solve the problem, find B in, find B out, so at point out what will be, what's P in will be. I will not solve this, maybe I'll solve these problems in the future, but I'm just saying that you can apply, we have problem of magnet, convert that problem to a current density using this that we use to develop this, formulas over here, and then you can knowing the solution to a problem, just currents, I can get this problem for the magnet. Okay, I'm not doing it, but I will do it sometime in the future. Okay. Okay, finally some material properties. We define some material, simple linear material properties. So if you look at this, if you say I'm going to write P polarization in terms of the electric field that I'm seeing there. So I have material, I'm at that point. Polarization is this P, electric field is E at that point, at same point. So I'll say more electric field, more polarized will be. So it's going to be something linear, and I'm going to define a property like this, E. If I define this and apply this is called so you have a electric susceptibility. So you can see that this is going to be, and so when you plug in there, you can see the D will simply be epsilon naught 1 plus chi E. Like as if D is proportional to A. And so this is called linear materials, linear polarized materials. If this guy itself depends on electric field, then becomes nonlinear. And similarly for H, you can see that I could do, I want to define H equals to, this thing here is another constant we can just bundle together. It's called epsilon instead of epsilon 0. So the epsilon will be this whole thing. You might know the name of epsilon 0 is permittivity of free space or vacuum, and epsilon is permittivity of the medium. And if you have epsilon over epsilon 0, so this is what is called dielectric constant. Okay, so I want to write, similarly I want to write 1 over H is some mu. Will be the permeability of B. So what would I go? You can see similarly I can define something like, if I define M is equal to chi M H, then if I use over there, I have a H equals to 1 over mu naught B minus chi M H, and then this says mu naught times 1 plus chi M H equals to B. And so if I bring on the other side, so this is what mu will be. It's kind of very similar. So chi M, that electrostatic chi will be magnetic susceptibility. Chi A is electric susceptibility. Okay, I'm going to stop here. It's going to be a really long video. In a next video, I'm going to take on some problems and try to do some problems in magnetized materials. All right? Okay, take care. Bye.